In this episode, I will introduce some concepts used in the presentation. First out is the concept of requirements. This is how we describe our expectations on how the system should work and behave. Then I will introduce some essential testing concepts, such as test steps and reactions. I will also talk about the difference between active and passive testing. Finally, I will present what I mean by different kinds of similarities. The goal of testing is to make sure that the system meets the requirements. Such requirements can look very different. Often, these requirements are described in a natural language like this one. This particular requirement describes the behavior of a train when a door is open. When a cab door is open, the traction should be blocked. To test this, a test engineer creates a test procedure, or called also a test case. A test procedure is a series of test steps with an action and a corresponding reaction. The action tells what to do, and the reaction tells what to look for in the system response. This observation is compared to a requirement to achieve a verdict that can be, for example, passed or failed. In this particular case, we have the actions to the right, and those are to start up the train, we open the left door, we try to start the train, and then we check that the traction is blocked, as is said in the requirement. If the traction is blocked, everything is fine, and we say that the test verdict is passed. And we note that in the test record. If it's not blocked, however, the verdict is failed, and we note that in the test record, and this probably goes back to the developers and need to fix it because it's probably a bug. Finally, we need to clean up the system and make the simulator or the hardware rig ready for upcoming tests. To better understand how test effort is spent, let's take a look at the test case placed on a timeline. The first action was to start up the train. Then we need to wait for a while to give the onboard systems a chance to start up. Then we open the left door. We wait for time to let the door open, and then we try to start the train. We wait and we check that the traction is blocked, and we note the verdict in the test record. Finally, we need to clean up everything. So what we can note here is that we actively command the system before checking each reaction. And we denote this kind of testing as active testing. So far so good. But to know how to reduce effort, we need to start the situation where we have more requirements to test. So let's take a look at another requirement. Requirement number 2 says that we should have extra heat as long as the door is open. Again, the requirement is tested using a series of test steps to the right. Start up the train, open the left door, check that the heat is on, and finally the cleanup. A1 and A2 are actually the same actions as for the last test case. We call such similarities action similarities. Can we save any effort using that knowledge? To understand that, let's put both requirements on a timeline and see if we can do this more efficiently. As you see in the figure here, test cases are often executed one after another. So to the left, we find the test for the first requirement, and to the right, we see the test for the second requirement. If we look a bit closer, we see that the first two actions are the same. So we can actually move the reaction test from the second test like this. Now the entire test case number 2 can actually be removed, and we have saved a lot of effort. So will this always work? Well, let's take a look at the third requirement. In this requirement, the traction should be blocked while the alcohol lock is denied. To test this, again, we have a series of actions to the right. Start up the train, fail the alcohol lock, and then we check whether the traction is blocked or not, just as for the first requirement. We call such similar checks reaction similarities. Now let's put these two together, the first requirement and the third requirement, to see if we can save an effort like we just did with the first and the second. This is a timeline for testing requirement 1, followed by testing requirement number 3. And the test procedure is as before. We start up the train, we wait for a while, we open the left door, we try to start the train, and if traction is blocked, we say this is a pass, and we clean up. For the third requirement, we start up the train, same as before, we fail the alcohol lock, and this is a new action. We try to start a train, same as before, and we check the traction, also same as before. And we clean up, and it's also same before. Now, let's naively merge these test cases as we did in the last example. So we move the traction check, and we move the alcohol lock action. And we remove the rest of the test case that we don't need. Okay, so what's happening here? Well, we do the right things and we do the right checks, but there's no difference between our two traction checks. In the current form, they were actually depending on the previous actions in the test procedure to know which requirement was tested. So this is one reason why it's difficult to parallelize active test cases, as we have done in these examples. So we need to know why traction was blocked to know which requirement actually was met. More precisely, we need to make the reaction part, or these traction checks, independent of the action part. So let's leave the action part for now and see how passive testing can help us with making these reaction checks more independent. Passive testing means that we observe the system without touching it. Thus, we need to make the reaction part independent of the action part when testing our three requirements. Our first observation is that requirement number 1 and 3 should assert that the traction is blocked, while requirement number 2 asserts that the heat is on. By only observing the corresponding signals, that is, the traction signal and the fan heat signals in this example, we find out whether a requirement is fulfilled or not. But we shouldn't do these assertions all the time. For requirement 1, asserting that the traction block is on is only meaningful to do while the cab door is open. We call such conditional assertions guarded assertions. The guard decides when, and the assertion decides what to check. Let's imagine that the tester has performed a realistic drive cycle while recording the signals cab door, alcohol lock, traction heat and fan heat. Does the system meet the requirement 1 during this drive cycle? Let's take a closer look. To test the first requirement, we assert the traction state whenever the door is open. The first time the door is open in our example, the traction was blocked all the time, and the test passed. The next time the door was open, however, only a part of the period is considered to be passed because the traction block was delayed for some reason. This means that the rest of the period has failed. This could easily have been missed using traditional testing, where we often perform a check only once. And in this particular case, that means that our verdict would depend on how long we wait. Here we would have got a fail, but if we only checked here, we would have believed that everything worked fine and thus missed the bug. In the same way, we see that we would get a pass for the second requirement in the first period, but then when the tester continues to drive, the test fails. And this would also have been missed if you have checked only once. For the requirement 3, you see that both of these tests are actually failed because they are partially failed in the same way. So notably, this passive approach allows us to save execution time as well as possibly find bugs earlier, because we can evaluate these tests in parallel, but also we test more of the time.